Hello, good morning everyone. Today we are going to discuss two important concepts, dependency preservation and canonical cover. While performing normalization, we have seen that we need to make use of functional dependencies. So with respect to the normal form that we are making use of, we need to properly use these kinds of functional dependencies for decomposing the original relation into the set of relations like R1, R2 up to Rn. So usually what we do is, while performing normalization, given a relation schema R, depending on the normal form that we are making use of, we pick the appropriate functional dependencies from the set of functional dependencies and we decompose our relation in R1, R2 up to Rn. Right? And what we want is, we want this decomposition to be lossless join decomposition. So we have seen in the last class what we mean by lossless join decomposition. If we are not having this decomposition lossless, or if we are having lossy decomposition, then the decomposition would result in information loss. And we do not want to lose any kind of information that is being stored in database. And that is why we want our decomposition to be lossless join decomposition. Secondly, we do not want any kind of redundancy. And that is the reason why we prefer one of the normal forms for performing the normalization. So the third important point that we are going to discuss today, as far as the good database design is considered, is preserving the dependencies while decomposing the relation. So what is dependency preservation? See, if we are having any relations, let us assume that we are having a relation R with say 3 attributes A, B and C, right? And let us assume that we are having a functional dependency, say A determining B. So whenever we are performing any update in this relation, what we mean by update, suppose I am inserting data in this relation. Then every time whenever there is an update in a relation, the functional dependencies in the set of functional dependencies are tested for its violation. Functional dependency actually is a constraint on the attributes of the relation. So whenever we are trying to perform any update in any relation, the related functional dependencies are tested for their violation. What does this mean? See, for example, let us assume that we are having one instance of this relation R. So as we are having 3 attributes A, B and C, obviously if I am inserting a tuple in this relation, I'll be inserting the values for A, B and C. Suppose initially my relation is empty and I'm inserting the values. Say for A, I'm inserting A1, for B, I'm inserting B1, and for C, I'm inserting C1. That will be all right, right? So we have inputted the first tuple. Now, if I try to insert one more tuple in this table, and if I'm inserting the data like insert into R values, say A1, B2, C2. Suppose I'm trying to insert these values in this relation. A1, B2, C2. So A1 is the value for A, B2 is the value for B, and C2 is the value for C. So as we are having this functional dependency that is imposed, this is my constraint, right? So A must determine B. So whenever I'm inserting this tuple, my system will check what is the value of A. It is A1, right? And I'm having earlier the value of A as A1. I'm having a tuple with value of A as A1. And for this tuple, I have inserted the value of B as B1. As I am having this valid functional dependency A determining B, what is important is if I am having two tuples in a relation, say T1 and T2, then this functional dependency says that if my A values are same, my B values must be same. Then and then only this functional dependency is satisfied. So always whenever we try to update our relation, our system is checking whether the functional dependency is violated or not. So if I try to input these values in my relation R, A1, B2, C2, then obviously what will happen? For these two tuples, value of A, that is A1, matches. Then if I am having this dependency A determining B, then I must have value of B as B1. But I am inserting value of B as B2. So this functional dependency is not satisfied. And that is why if I try to insert such kind of a tuple in my relation, this tuple will not be accepted because it is violating my functional dependency A determining B. Right? But instead, if I try to input the data like A1, B1, C2, then obviously the system will check whether A is determining B. Yes, for attribute value A, for attribute A, if the tuple is having value A1, then my value of B must be B1 and I am inputting the same. So there is no violation of functional dependency. And that is how this particular tuple, if I try to insert A1, B1, C2, will be accepted. Why? Because this functional dependency is not violated. Right? So every time, whenever we are having any update in a relation, the functional dependencies are being checked for its violation. Now, if every time these functional dependencies are being checked, obviously what we would like to have is, we would like to have this efficient checking of violation. So we want to have a system such that this testing of functional dependencies for their violation is efficient. And if we want this testing of functional dependencies efficient, what we want is, we want to preserve the dependencies. So what we mean by dependency preservation? While testing a functional dependency for its violation, we do not want to compute a join of the relations. I'll repeat what we mean by dependency preservation. Every time, whenever there is any update in the relation, we are testing FDs for violation. Right? And whenever we are testing these FDs for violation, we do not want to compute any join of the relations. So no computation of joins. What does this mean? While testing the functional dependencies dependency, say for example, A to B is the functional dependency. And if I want to test it, these attributes must belong to the same relation. Right? If I am having, say for example, if I am having a dependency, say A to D, and if I am having another relation, say S, wherein I am having two attributes, say D and E, right? And I am having the dependency like A determining D. So if I want to check for the violation of this functional dependency, A determining D, these two attributes do not belong to a single relation, right? A belongs to relation R and D belongs to relation S. So if I would like to test for this functional dependency, what I need to do is I need to compute a join of these two relations R and S. And then only it would be possible for me to test for that functional dependency, right? And computation of a join is expensive. So we do not prefer to compute a join for testing the functional dependencies. So under dependency preservation, while testing the functional dependencies, we try to have a decomposition such that for testing the violation of functional dependencies, we need not compute join of relations. Right? Are you getting me? Yes?
Yes, ma'am.
Yes,
Fine.
ma'am.
Fine. So, let's extend our discussion now related to this dependency preservation. So, formally, what we are going to, or how we are going to test this dependency preservation. So, we are having the original set of F, right? This set of F comprises of the functional dependencies. Those exist, right? Now, we know using this F how to compute the closure of F, that is F plus, right? So we know F plus also. So given the set of functional dependencies F, we can compute F plus, right? Now, let us assume that we are creating a new set of functional dependencies Fi. And this Fi is the set of dependencies in F plus that include O in Ri. So what does this mean now? See, I am having the relation R, original relation, and that relation is being decomposed in R1, R2 up to Rn, right? So in general, I am saying that this relation is Ri. So every relation in this decomposition is having some set of attributes. Do you agree with me? Yes? Do you agree with me? We are having original set R, right? And we are decomposing this relation R into the set of relations R1, R2 up to Rn. So, we know that R is given as R1 union R2 union R3 up to union Rn, right? So whichever are the attributes of original relation R, those attributes are being distributed in these n relations. Do you agree with me?
Yes, ma'am.
Yes, ma'am.
Right. So this every relation is now denoted as array in general. Okay. Now, given this R, we are having the set of functional dependencies F. And with this set of functional dependencies F, we can compute this F plus. And now we are deriving a new set of functional dependencies denoted as Fi. So in our F plus, what we are having is, we are having all the functional dependencies, those exist for this entire schema R. Right? So obviously, if I am having this F plus comprising of all the functional dependencies, those are applicable for this original relation R. I am having a huge set. Right? And after decomposing this relation R into say R1, R2 up to Rn, obviously we have attributes in those relations. So few of the functional dependencies from F plus are actually referring to the attributes from array. I'll repeat. Few of the functional dependencies from F plus are actually referring to the attributes in array. Right? So similarly, for every relation Ri, in this decomposition, we may come up with a set of functional dependencies Fi that include only the attributes in relation Ri. And this set Fi is known as the restriction of F to Ri. The restriction of F to array. So Fi includes only the attributes in our relation array. So if I am having n number of relations, I'll be having n number of such restrictions of F with respect to the relation array. Am I clear? Yes.
Yes, ma'am.
So with respect to every relation in decomposition, now we have a set of functional dependencies Fi that includes only the attributes in array. Right? Now, under dependency preservation, we need to follow one condition. And what that condition is, whenever we try to decompose our original relation R into the set R1, R2 up to Rn, we are computing the respective sets of functional dependencies F1, F2 up to Fn. So with respect to this Rn, R1, I am having F1. With respect to this R2, I am having F2. With respect to this Rn, I am having Fn. Right? So preferably, the decomposition should be dependency preserving. Meaning, if I try to compute the union of those individual sets F1, F2 up to Fn, and if I try to compute the closure of these unions, then this closure must be same as the original closure F plus. If this condition is satisfied, then we say that our decomposition is dependency preserving. Otherwise, checking the updates for violation of functional dependencies may require computing the joins. And computation of joins, as I stated earlier, is very expensive task. So we do not want to compute the joins for testing the violation of functional dependencies. And that is why we need to impose this condition of dependency preservation while decomposing our original relation into set of relations. And the condition that should be satisfied is the individual sets F1, F2, Fn. If we find the union of these individual sets, obviously we are coming up with one more set. So we are going to compute the closure of that set, and that must be equal to the F plus. That means the closure of the original set of functional dependencies. Now, to understand it better, once again, I'll be giving you one example. Right? Say, for example, we are having once again these two tables or these two schemas R and S. Right? R comprises of three attributes A, B, C. S comprises of two attributes D and E. Right? And we are having the set of functional dependencies. And what is that set of functional dependencies? Let us assume F is equal to, say, A determines B, B determines C, and suppose A determines D and D determines E. So, in my set of functional dependencies, let us assume that we are having these four functional dependencies, right? And let us assume now that this is our set R1 and this is our set R2. Okay, now what we are going to test is, so my original relation R are having 5 attributes A, B, C, D and E is decomposed into these two relations. R1 with 3 attributes A, B, C, R2 with 2 attributes say D and E. And we have been provided with this set of functional dependencies. Right? Now, according to our discussion of dependency preservation, if I know this F, it is possible for me to compute F plus. Okay, now what we are saying is, with respect to this R1, we will be forming this set, the restriction of F to R1, and this set is denoted as F1. So what this set F1 will have? This set F1 will have only those functional dependencies from F plus, those have the attributes belonging to the respective relation R1. Now, instead of having this set F1, we have not yet computed F plus. So, let us prepare this set F1 with this F itself. So, F1 will have the functional dependencies such that these dependencies will have the attributes only from R1. So, if I check this A to B, whether both the attributes belong to R1, yes. So, in my F1, I'll be having this functional dependency A to B, right? Now, I'll check next functional dependency B to C. Whether B and C both are available in R1, yes. So, once again, this B to C can be included in this F1. Now, what about this A to D? We are having two attributes A and D. A belongs to R1 and D belongs to R2. Right? So if I am having such kind of a functional dependency such that both of these attributes or all the attributes in that functional dependency are not part of R1, then I'll not include that functional dependency in my F1. Right? So this functional dependency will not be included in F1. Okay? Now, if I talk about this F2, with respect to this F, I am having in F2 this functional dependency D to E. This A to D cannot be included in F2 also because D belongs to R2 but A belongs to R1. Are you getting me? Yes?
Yes, ma'am.
Yes, yes, ma'am.
Fine. Now, according to our condition, what we want is, we want to compute F1 union F2. And then we want to compute the closure of that. Right? And we want to have this closure equivalent to our F plus. If this condition is satisfied, then only we will say that the decomposition is preserving the dependency. Okay, now please see here. My F1 union F2 will have these three dependencies. Right? And if I try to compute now closure of this set of dependencies, wherein I am having these three dependencies, it is not possible for me to have this A to D in that. But in my F plus, which is the original set of functional dependencies, in my F plus, I am having this A to D dependency. But if I try to compute the closure of the restricted sets, then I may not have this dependency in this closure of F1 union F2. So in this particular scenario, I may say that F1 union F2 closure is not equal to my F plus. And if this is the case, then obviously this decomposition is not preserving dependencies. Are you getting me? Yes?
Yes, ma'am.
Got the concept? Yes.
Yes, ma'am.
Ma'am.
Any doubt?
No.
May I proceed?
Yes, ma'am.
So I hope now.
Yes, ma'am.
Okay. So I hope now you must have understood the concept of dependency preservation. Right? So let us go through one example so that once again we can focus upon these two concepts of lossless joint decomposition and dependency preservation. Let us assume that we are having this relation R with three attributes A, B and C. Okay, now my set of functional dependencies F that is provided. This F includes two dependencies, A determining B and B determining C. Right? So in our set F, we are having these two functional dependencies. Okay, now this relation we would like to decompose. So this relation can be decomposed in two different ways. So what are these two different ways of decomposition? In the first decomposition, I'll be having R1 comprising of two attributes A, B R2 comprising of two attributes B and C. Okay, so this is one way of decomposition. Now, let us try to find out whether this decomposition is lossless join decomposition and whether this decomposition is dependency preserving. So we want to answer now these two questions. We have decomposed this relation R as R1AB, R2PC. We have been provided with this set of functional dependencies F. We would like to find out whether this decomposition is lossless join decomposition, and also we want to find out whether this decomposition is preserving the dependencies. Yes, anybody who can answer? In the last class, we have seen the concept of lossless join decomposition. So what we said, when we say that the decomposition is lossless join decomposition, we try to find out the intersection.
Common.
Yes, we try to find out intersection of R1 and R2. So here, what is my intersection of R1 and R2? Yes?
B.
B.
Right. So I am having B as the intersection. Now, to find out whether this decomposition is lossless join decomposition, we need to test one condition. And what that condition is, either my R1 intersection R2 should determine R1 or R1 intersection R2 should determine R2. So if one of the dependencies is satisfied, then we can say that it is lossless join decomposition. Right? So this intersection must be the super key of either R1 or R2. Okay, now let us test whether this B is super key for this R1. How to find out whether B is super key of R1? We have been provided with set of functional dependencies F. Right? And if you remember, once again, I am repeating those concepts because these are very important concepts. If I am having set of attributes, say K, and if this set of attributes determines every attribute in my relation R, then I may say that this K is my super key. Am I correct?
Yes, ma'am.
Fine. So now we want to test whether this R1 intersection R2, that means this attribute B, whether the attribute B is super key of R1 or R2. Yes. Whether B is super key of R1 or R2.
Yes, ma'am.
Is it the super key of which relation? Is it so difficult?
R1.
B is super key of, see, if B is super key, B should determine my R1 or B should determine my R2. When I will be saying that B is the super key of R1, if B determines R1. When I'll be saying that B is super key of R2, if B determines R2. Now what is there in R1? In R1, I'm having two attributes, A and B. So whether B is determining A and B, whether B determines A, B determines B, but whether B determines A,
No.
no, because in our functional dependency, set of functional dependency, the dependency that exists is A to B, A determining B, but B is not determining A, right? So B cannot be the super key of R1. Now, let us check whether B is super key of R2. When we will be saying that B is super key of R2, if B determines both the attributes B and C. Correct, na? So B should determine B. Yes, obviously. Whether B determines C.
Yes.
Yes, it is given. Right? So we may say that B is the super key for this relation R2. So this condition is satisfied. Right? And that is why we may say that this relation, or rather this decomposition R1, R2 is lossless join decomposition. Do you agree with me? Yes?
Yes.
Yes, ma'am.
Got it? Very important concepts. You will be having similar kinds of examples to solve in your exam. If you have any doubt, please let me know. So have you understood why we are saying that this decomposition is lossless join decomposition? Yes. Any doubts so far?
No,
I
ma'am.
think no, ma'am.
Okay. So now this decomposition, we have found that this decomposition is lossless join decomposition. Now let us try to check whether this decomposition is preserving the dependencies. Whether this decomposition is preserving the dependencies. And how to check it out? A simple way to check it out is whatever is the set of functional dependencies given. Okay, we need to check F1 and F2 associated with this R1 and R2. Okay, so restrictions with respect to R1 and R2. So F1 will comprise of only the dependencies having the attributes from R1, and F2 comprises of only the dependencies from F plus. Those belong to this R2 only. Right? Now, if we try to find out the dependencies, see here, I am having A to B, and here I am having B to C. Is that correct?
Yes.
So, if I try to compute F1 union F2 and closure of that, it will provide me F plus. Okay, so to test for any functional dependency from this list, I do not need to compute a join. A to B can be tested with this R1, B to C can be tested with this R2. So I need not test a dependency after computing the join of these two relations. And that is why I may say that this decomposition is dependency preserving as well. Okay. Now, let us see another kind of decomposition. See here, we may decompose this R in this manner also. R1 comprising AB and R2 comprising AC. Now, if we look at this decomposition, whether this decomposition is lossless joint decomposition and whether this decomposition preserves dependencies. So once again, we need to apply the same conditions, those we have discussed right now. Whether this decomposition is lossless joint decomposition. So what we need to check? We need to check R1 intersection R2. So in this case, what is R1 intersection R2?
A.
A. Right. Now, what we need to check? Whether this R1 intersection R2 determines R1 or whether R1 intersection R2 determines R2. That means we need to check in this case whether A determines AB or whether A determines AC. Now, let us check whether A determines AB. Yes. We need to refer to this set of functional dependencies F. In F, we are having the dependency A to B. Right? So, A is determining B. And what about A to A? Obviously, yes. A always determines A. Correct, na? It is reflexivity. Right? So, A always determines A and A determines B. It is given. So, this is satisfied. So, R1 intersection R2 is giving us A and A is the super key for R1. Right? And that is why this decomposition is also lossless joint decomposition. Right? But whether this decomposition is preserving the dependencies, that we need to check. Now, what is the dependency that we have? A simple trick I am giving you. A to B. So whether A to B can be satisfied without computation of join of these two, R1 and R2. See, what we need to check is, check whether functional dependency is or can be tested without computation of a join. So if I want to test for A to B, whether I need to compute a join of R1 and R2 to test for A to B?
No.
No, right. So A to B can be tested without computation of a join. Now, the next dependency is B to C. Whether this dependency can be computed without computation of a join of R1 and R2? Yes. B is in R1, C is in R2. So both of these attributes are part of two different relations. So if we want to test this functional dependency, we have to compute the join of R1 and R2. Otherwise, it is not possible for us to test for this dependency. Do you agree with me?
Yes, ma'am.
So,
Yes, ma'am.
what we can conclude now? Whether this decomposition is preserving the dependency?
No.
No. So, this decomposition is not preserving the dependency because we cannot check the dependency B determining C without computation of the join of R1 and R2. Right? So, if this is a relation and if more than one solutions are possible for decomposing that relation, we should prefer a decomposition that is lossless join decomposition and which is preserving the dependencies. Right? So, in these two cases, we should pick this particular solution. Right? Is there any doubt so
Yes,
far? Yes?
No, ma'am.
Fine.
No, ma'am.
Okay.
No, ma'am.
Right. So, now this is the exercise for you. You please pick the correct answer. We have the set of FDs B to C, C to A and B to D for the relation schema R given as A, B, C, D. Which of the following decompositions has the dependency preserving property? 4 options are given A, B, C, D. So pick the correct option. Yes. Which is the correct option?
C.
C. Why? How C? You justify your answer. What we want as the condition to check. Given the set F, right? What we need to do is we need to test these functional dependencies for violation. Right? And while testing these dependencies, we need not have a join of the relations. So if you are saying that answer is C, then see the first dependency B to C. If I want to check this dependency B to C, then this is my R1 and this is my R2. Whether I need to compute a join to test for B to C?
Yes.
Yes. Correct, na? Because B belongs to this relation R2 and C belongs to this relation R1. So these attributes are part of two different relations. So if I want to test for this dependency, I need to compute a join of these two. So C cannot be correct. Getting me? Yes?
Yes, ma'am.
What about B? Once again, see
No.
here, ACD and BD. If I want to test B to C, I need to compute a join. Correct, na?
yes, ma'am.
Yes, ma'am.
So that may not be the answer. What about this A?
Yes, ma'am. I think that's the right answer. C to
So,
A there is direct.
so C to A, B to C can be tested with this. C to A can be tested with this. B to D can be tested once again with this. Right? So we need not have, or we need not compute a join of these two. But please remember, right now we are using a trick, and that trick is we are only checking for F. In fact, we need to test for F plus. Right? But to simplify our task, initially we test for F. So in F itself, if we find any functional dependency that is not violate or that is violating, then directly we can discard that decomposition. Right? So initially we begin our testing with F, and if required, then only we go for F plus. Right? So this is a trick that we may use. Actually, as per definition, we need to compute our F plus. But as you know, computation of F plus is also lengthy. Right? So to simplify the task and to come up with quick answer, what we can do is we can initially test for F, and then only we may go for F plus. Right? So the correct answer for this question is option A. Right? May I proceed?
Yes.
Yes,
Fine.
ma'am.
Yes, ma'am.
Fine. So now I'm going to introduce you one concept, and that is known as canonical cover or minimal cover, and then we'll conclude our session, and the detailed discussion of canonical cover can be presented in the next session. So what is minimal cover and what is the need of having the minimal cover, or it is also known as canonical cover? Many times the sets of functional dependencies, those are provided F, have the redundant dependencies. Those can be inferred from other dependencies. What we mean by that? Say for example, if this set of functional dependencies is given A to B, B to C and A to C, then in fact this A to C is redundant. Why? Because if I have A to B and B to C, I can infer A determining C. Are you getting me?
Yes, ma'am.
Fine. So many times it happens that whenever the set of functional dependencies F is being provided, we find that there are several dependencies, those are redundant, or those can be inferred from other functional dependencies. Right? Even sometimes we find the functional dependencies such that the part of functional dependency is redundant. Not entire dependency is redundant, but the part of functional dependency is redundant. Right? So, for example, if I am having this set of functional dependencies A to B, B to C and A to CD. So this dependency can be or rather this set of functional dependencies F can be simplified as A to B, B to C and A to D, where this attribute C is extraneous. This attribute is extra, and even if we do not use that attribute, it is possible to infer this A to CD with the help of these three functional dependencies. Similarly, if we look at this set of functional dependencies A to B, B to C and AC to D, this set can be simplified as A to B, B to C and A to D. So here in the left hand side of this functional dependency, this attribute C is extraneous. So even though we we omit this attribute C, it is possible for us to derive this dependency AC to D, right? So, in essence, what I would like to emphasize is many times it happens that given the set of functional dependencies F, there are chances that few of the functional dependencies are redundant or those can be inferred from other dependencies, or some part of functional dependencies may be redundant. So we have seen the example. Few of the attributes are extra, redundant. So we can omit those attributes and we may come up with a simplified set of functional dependencies. Right? Now, whatever we do, we should ask one question. Why? Why we are doing this? Why we are finding whether the dependencies or part of dependencies are redundant? There should be some motive. There should be some goal behind every task that we perform. Right? So here also, why we are discussing this concept? Because we would like to simplify our original set F of functional dependencies, and we need to come up with a minimal cover or a canonical cover of the set of functional dependencies. And the reason is, see, for example, I'm giving you one reason or one example here. As I stated earlier, to check for dependency preservation, or anyhow, whenever we try to update our database, each functional dependency in set F is being tested for its violation. Correct? So if I'm having this set F, A to B, B to C and A to C, then every functional dependency will be tested for its violation. So my system will check whether A to B is satisfied, whether B to C is satisfied, whether A to C is satisfied. Right? So three functional dependencies are being tested. But now, as I stated, this functional dependency A to C is redundant. Right? So we can infer this from these two, A to B and B to C. So if I am having this redundant functional dependency, there is no need to once again test this. Right? So if I am omitting such redundant dependencies from my original set F, then I may come up with a simplified set of functional dependencies. And why we require such a minimal set? The reason is, while testing the violation of functional dependencies, if I am testing minimum number of functional dependencies, it would be less expensive. Rather than testing 3 dependencies, if I am testing 2 dependencies, then obviously it is meaningful. Right? And that is the reason why we are computing this minimal cover or the canonical cover of set of functional dependencies. So, a canonical cover of set of functional dependencies F is a minimal set of functional dependencies equivalent to F, having no redundant dependencies or redundant part of dependencies. And one more condition that we will discuss next in the next session is, if I am having original set F and if I am having canonical cover FC of F, which is a minimal set, then F plus is same as FC plus. Right? So I'll define once again what is canonical cover. A canonical cover of F is a minimal set of functional dependencies equivalent to F, having no redundant dependencies or redundant parts of dependencies. Right? So, I hope you must have understood this concept. We are going to extend our discussion about canonical cover in next session. Right? Am I clear? Yes?
Yes, ma'am. Yes, ma'am.
Fine. So, let's conclude the session today. Thank you.